Hello, today we'll talk about a subject that doesn't really fit in with anything. It's kind of, I guess it's a mechanical engineering type of discussion, and I'm going to call it screwing up stuff. Because we want to know how stuff changes when we apply weird forces to it. We want to screw up stuff. They call it in the book solids and elastic deformation. Now, elastic means that it's deforming in a predictable way. Like if I pull this, it'll go whoop, and it'll go back to where it was. Whoop, and back to where it was. So there's a restoring force and everything is happy, and the fundamental structure of this piece of foam isn't going to change. If I pull it too hard, then I'll go out of the elastic regime and into the plastic regime where it will be permanently damaged. But I'm not going to let that happen because I want to predictably screw up stuff and reversibly screw up stuff. So here we go to our first bit of screwing up stuff. Here's a wall, and I want to bolt a cylinder to it. So here's my cylinder of stuff that I'm planning to screw up, and I want to apply a force to this stuff. Well, it's starting out with an initial length of L naught. And I want to apply a force to it, and that's going to cause it to lengthen. And it will be here later on. And that change in length is what I'm going to be, well, presumably measuring or something, and that happens when I apply a force here, and let's just call it F, that force that way. Of course, if it's bolted to the wall here, put some bolts on here. Bolts should be purple. Bolts are there, and it's bolted to the wall here, so it can't move at all. And if it's bolted, then there's an equal and opposite force this direction that's keeping it on the wall. So the thing is in equilibrium, but it's feeling a stretching force of F. So what you need to know is that there's this structure, and I'm not going to say that everything is simple cubic, but generally you might have atomic bonds that look like this that form material. So, yeah, I guess there are some back behind it too, but those will clutter us up. We can draw them in a different color maybe. Oh boy, this will be interesting. There's probably another atom back there. There, all right, good. So if you stretch a material, that means that these atomic bonds, some of them are stretching a little bit. And the idea is we can figure out what delta L might depend on. This delta L right here, let's go brown. Delta L, well, it's going to be proportional to some stuff, right? And delta L is probably going to be proportional to how long it is. Let's see if that's reasonable. Do you think that if I stretch this, I will get a delta L for some force? What if I try to stretch just a quarter as much? Do you notice that I'm not getting as much of a delta L? Sure, I get a bigger delta L if I stretch it when it is longer. Foam everywhere, dang it. Okay, so it's probably going to be proportional to L naught. Do you think it will be proportional to how much I'm pulling? Yes, of course it will. Sure. What else? Ooh, what about this? What about the cross-sectional area? Do you think that this will stretch just as easily as this will stretch? Which one stretches more easily? Do you notice that? I'm thinking it's pretty obvious actually. This one has much more cross-sectional area, that would be this area right here, than this one does. Tiny area, big area, okay. And so I guess it makes sense that the one with the bigger area stretches less and the one with the smaller area stretches more, so it's not going to be proportional, but rather inversely proportional to the cross-sectional area of the thing. So we should call that sucker out. That's going to be our cross-sectional area. And, well, now we've got ourselves an equation. And if we say, well, I'm going to reformat it a little bit. I'm going to say that F is proportional. This force, it doesn't really make sense, but really I like this formatting right here. But this variable we're going to define is built in a different way. Force is proportional to, well, delta L over L. See, I'm going to divide by L naught here on both sides. And then I'll put that sucker in parentheses, and then I've got an A up in the numerator this time. And instead of writing a proportionality, I'm going to say that force is equal to a new variable, which I'll call Young's modulus. You ready for Young's modulus? Let's go orange for Young's modulus. Young's modulus. Young's modulus tells you fundamentally how much the structure, does or doesn't like being stretched. Let's figure this out. Where would Young's modulus go in this equation? If I were to solve it like this, I guess it'd be on the opposite side. It'd be over here, or it would be here. So delta L, Young's modulus, big Young's modulus. Look at this, I can make this an equal sign. Big Young's modulus means that delta L will be small, and small Young's modulus means that delta L will be big. So I guess that means that Young's modulus is the toughness of the material. A big Young's modulus describes something that really doesn't want to stretch. Let's see what the units of Young's modulus need to be. The units of Young's modulus, I need to get force out, and over here I've got units of 1, no units here at all, times area. So it's going to have to be force divided by area. So that is newtons divided by square meter. Ooh, interesting. That looks like a pressure. Well, that's kind of funky. Okay, all right, let's keep going. I want to screw up stuff in another way. Yeah, let's try screwing up things. I'll leave that there for reference because I'm probably going to look at that. Let's try screwing up something like a book. The interesting thing about a book, sorry, my hands are really cold. The interesting thing about a book is that if you put it like this, you can screw it up like that. And that's shearing. Check it out like this. I'm not sure if this is going to focus, but I can push like that and it shears the book because I'm putting one force this direction and the other force that direction. Shoop, shoop. Yeah, and we could try to think about what might affect how easily a book shears. So to do that, I will draw you a book. That was a blue-bound book. Let's put it as a blue-bound book. Here's our blue-bound book, and it's got pages in here, and there we go. And I want to say that, well, we need to force this direction. What were my forces? My forces were blue, light blue. I want to force this direction on the bottom and a force this direction on the top. And what's going to happen is sucker's going to bend a little bit. And I'm going to get this pattern. The bottom's going to stay where it was, and the book's going to be like that. And this distance right here, let me call this distance out. This distance right here is delta x, the change in the position of the top of the book, because the bottom of the book is presumed not to have changed position. Let me color in these leaves over here. Now, the whole book has shifted a little bit. I hope that makes sense. I hope that you could see that with me shearing the book. And I want to try to figure out what, again, what delta x depends on, in very much the same way as we did with delta L. So delta x, how much the book has shifted, well, I guess it's going to depend on how long the book is. But wait, do I mean this direction? I don't really think this has much to do with it. What I really mean is how thick the book is, and I'm going to call that the initial thickness of the book, L naught. It depends on L naught, so delta x is going to be bigger if the book is thicker. You notice this with small books. With small books, you have very little tendency to shear, and with big, really thick books like phone books, you can shear those suckers like crazy because they're so tall. And with the Oxford English Dictionary, if you could get that 2-volume set of that sucker, it's like this thick. I want one of those. Then you push on the top, and that sucker will shear super easily. Now, don't do it to your OED because that's a lovely book. But do it to a phone book, for instance. And I guess delta x will get bigger if I apply a bigger force. That's pretty obvious, so I'm going to put force up top also. Now, what about, remember the previous one we had an area? Do you think that the area of this sucker, I'm thinking about the cross-sectional area, or maybe like the top area, slice it like this. If that's my area, if the area of the top is what matters, then probably a larger area will give us a larger shear. And for that purpose, I think I'd like to present these two to you. Here I can hold this one still and apply a force that direction at the top, and it shears very easily. Shear. And this one, I'm going to hold the bottom and apply a force at the top, and it shears much more trickily. It doesn't shear as well. This guy shears very easily. Whoop. This guy shears much less because this one has about 4 times the area as that one does. So I would imagine that this would be 4 times less easy to shear. And the way of showing that is that we are inversely proportional to the cross-sectional area in the same way as we were last time. I hope that's not too much of a surprise. I'm going to do the same thing where I solve this for force. And I'll do that in blue again. My force now is equal to some stuff. It's going to be, it's going to be delta x over L naught, and I'll put that in parentheses. Notice how because they're not in the same direction, delta x and L naught are not in the same direction, it doesn't make sense for me to call this delta L like I did in the last one, because I'm not linearly stretching the sucker, but I'm shearing it, pushing it to the side. And, oh, you know that some people call scissors shears? Let's see if we can figure out why that is. I think I've got a pair of shears in here. Yes, I do. Because their job is to shear stuff. Do you see how one of them is pushing up on the thing and the other's pushing down on the thing? And guess what? When you shear paper, it cuts. Yeah, because I've reached the plastic limit on that paper, and so it's beyond the elastic limit, and it's not coming back to where it was. So we have this cool flap. That's handy for the future. I wonder if I'll be able to work that in. Probably not. I'm solving for force, so area will be over here. The larger the area, the more force that will be required to get a given effective shear of that sucker. And, well, there's all this stuff, but then there's this constant that describes how unwilling the material is to shear. And I'm going to call it get ready, I'm going to call it the shear modulus. S equals shear modulus. So, too bad nobody got it named after them. Because Young had his Young's modulus over here, but shear, there's nobody named shear. Shear is just the thing. So let's look at the units of shear modulus. Units of shear modulus have to be, let's see if we can solve this sucker for S. We solve this sucker for S, I'm going to get S equals F over A times, well, it's going to be L naught over delta X. And so, dang, again, it's units of force over area. So this is newtons divided by meter squared. Again, dang. Oh, look, we've got it down here. Let's put it over here too. Newtons per meter squared. Sure, and so we confirm again that shear modulus is the tendency of something not to be sheared. It doesn't like shearing, so it would have a large shear modulus. And you can also, oh dang, one time I was cutting on a table saw and I slid my work over. No, I was trying to adjust the, there's a fence on the table saw, and I was trying to adjust the fence, so I was pushing on it, and I had my hand on the fence, and the thing is, there was this little notch, and it was like this, and that's where the pushing bar slides in the table saw. So I'm pushing this thing that's like this, and I'm pushing it that direction, and so my fingers were right here. Can you imagine where this is going? My fingers were right here. I'm not very good at drawing the human hand, but my fingers were right here, and I was pushing that direction, and guess what? This little bit of my finger right here remained at the bottom when I was finished, and blood was everywhere. It was not pink, but that's all I've got. There was blood over here, and there was blood over here, and there's blood over here. It kind of filled up this thing right here. It's really gross. Okay, the next thing that we should talk about is changing the volume of a thing. And I guess we could do that by changing the exterior pressure. So I'm going to start with some bulk thing, and I'm showing its initial volume right now. This is V naught. And then if I apply a force all over the outside, which would be determined by a pressure, then that sucker will go in. Remember how I'm drawing my forces with that blue? Let's go like this. Da, 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 da. And it will retain a similar shape, but it will be blob-like, and it will go to this sort of a volume, perhaps. And I'm going to call that VF. Okay, so the pressure changes the forces on the outside, and this bulk thing ends up shrinking. Suppose that's pretty reasonable. If I were to make an equation to try to study how the volume changes, would you hopefully, I hope that you would agree, that the volume change would be proportional to the initial volume? Yep. And what else? What's actually changing the volume? Well, obviously, the pressure change is changing the volume. So I'm going to put a delta P right here. And in fact, that's really all there is in this situation. It's a pretty simple situation. So I'm going to ask you to then say, what if I were, oh wait, delta P is the analogy of the force. Let's get the same equation up here. If I look at this equation, delta P is what I'm doing differently. The force is what I'm doing differently. And so there's a response to it. So I'm going to solve this for delta P in the same way as I solve this equation for force. And then I get delta P equals, well, I'm going to have a constant in here pretty soon, but delta P is the change in volume divided by V naught. So there's this thing. And then I have to define a bulk modulus. Again, there was nobody named bulk, but we can define the bulk modulus right here. And there's a minus sign. Why would there be a minus sign? If the pressure increases, do you expect the volume to also increase? You expect a minus sign. So I'm going to get a minus sign right here. And B, well, the units of this B thing, oh, check this out. The units of B, let's get a little equation going for B over here. I find B to be, well, it's going to be delta P with a minus sign in front of it, and then V naught over delta V. That stuff right there has no units at all. Delta P, change in pressure. Pressure's force divided by area. This has no units at all. The units of bulk modulus are also newtons per square meter. So we've got units of shear modulus that are newtons per square meter, and we've got units of Young's modulus, that was changing the length of a thing, that are newtons per square meter. The units of all of these things are the same. They're pressure units. That's really cute. At this point, that's all I've got. They all have the same units, and they all have this analogy, and we can talk about shear, and we can talk about bulk volume changes, and we can talk about a force that's stretching a thing. And we can put that all into the language of stress and strain. And I'm going to do that more carefully in class. But I do want to define stress versus strain. A stress is the applied force per area. Applied force per area. Okay? And a strain is how the system responds. And in general, I can say that stress divided by strain, let's see. Stress is the applied force per area, so that would be like this. And strain is delta V. Stress divided by strain looks to be something like this modulus. And the modulus modulates how much the thing responds to a certain stress. And, maybe you use these words interchangeably in your everyday life. Stress is kind of something that you're feeling stressed. Strain is how you respond. So this is cool. This has to do with studying and stuff. Also, you can be like, I'm feeling really stressed. Or you can say, however, I am straining very well because I am getting the job done. Goodbye. Hello, today we'll talk about a subject that doesn't really fit in with anything. It's kind of, I guess it's a mechanical engineering type of discussion, and I'm going to call it screwing up stuff. Because we want to know how stuff changes when we apply weird forces to it. We want to screw up stuff. They call it in the book solids and elastic deformation. Now, elastic means that it's deforming in a predictable way. Like if I pull this, it'll go whoop, and it'll go back to where it was. Whoop, and back to where it was. So there's a restoring force and everything is happy, and the fundamental structure of this piece of foam isn't going to change. If I pull it too hard, then I'll go out of the... It'll be proportional to how long it is. Let's see if that's reasonable. Do you think that if I stretch this, I will get a delta L for some force? What if I try to stretch just a quarter as much? Do you notice that I'm not getting as much of a delta L? Sure, I get a bigger delta L if I stretch it when it is longer. Foam everywhere, dang it. Okay, so it's probably going to be proportional to L naught. Do you think it will be proportional to how much I'm pulling? Yes, of course it will, sure. What else? Ooh, what about this? What about the cross-sectional area? Do you think that this will stretch just as easily as this will? Cubic, but generally you might have atomic bonds that look like this that form material. So yeah, I guess there are some back behind it too, but those will clutter us up. We can draw them in a different color maybe. Oh boy, this will be interesting. There's probably another atom back there. There, all right, good. So if you stretch a material, that means that these atomic bonds, some of them are stretching a little bit. And the idea is we can figure out what delta L might depend on. This delta L right here, let's go brown. Delta L, well, it's going to be proportional to some stuff, right? And delta L is probably going to be elastic regime and into the plastic regime where it will be permanently damaged. But I'm not going to let that happen because I want to predictably screw up stuff and reversibly screw up stuff. So here we go to our first bit of screwing up stuff. Here's a wall. And I want to bolt a cylinder to it. So here's my cylinder of stuff that I'm planning to screw up. And I want to apply a force to this stuff. Well, it's starting out with an initial length of L naught. And I want to apply a force to it, and that's going to cause it to lengthen. And it will be here later on. And that change in length is what I'm going to be, well, presumably measuring or something. And that happens when I apply a force here. And let's just call it F, that force that way. Of course, if it's bolted to the wall here, put some bolts on here. Bolts should be purple. Bolts are there, and it's bolted to the wall here, so it can't move at all. And if it's bolted, then there's an equal and opposite force this direction that's keeping it on the wall. So the thing's in equilibrium, but it's feeling a stretching force of F. So what you need to know is that there's this structure, and I'm not going to say that everything is simple.